by some law, and let defines that set of functions J, and we can say that the functional is defined in the class M by the law or rule J equal to J of Y of X. So here we can say this J of Y of X that contains the set of functions. In earlier, we are taking function of f of x, that is the set of all variables, means f is a function of x only. Here J is a function of functions, that is Y of X. So we can say it's a family of functions or this functional rules. If I take a rule here first, suppose you are taking M, a class of functions. That class may be like this, C of 0, 1. That means set of all continuous function within a certain interval 0, 1. Okay. So first we are taking an example where the set of functions that satisfy the continuity within an interval 0 to 1. So here you can say M equal to C0, 1 with a class of all continuous function which defines on the interval 0, 1. And then try to define J of X or J of Y of X. Suppose you are defining J of Y of X by this rule 0 to 1 Y of X dx. So the objective behind this, we are taking integral. That means while we are integrating or while we are taking an integration, it generally defines an area. Okay, and whatever the functions associated with the integration, that functions will lie in the area that lies between two values x equal to a and x equal to b, and below the curve y equal to f of x. That means we are taking the set of all functions that lies within that area. So here, in all the cases or in all the calculus, in variational calculus, we have to bind the functions with the rules of integral only. Okay, so j equal to j of y of x, that's equal to 0 to 1 y of x dx. It's a function of, and this is the class of function. That means the functions we are choosing, that function must be continuous within the interval 0 to 1. Okay, this is only an example here. So if we are forming the function like this, and the set of functions be like this, then we can find out the value of this functional. That is, if we find j of 0, it gives 0. If we find j of 1, that means in place of y of x, we can substitute 1. So if you substitute y of x equal to 1, you can get the value of j of 1 as 1. Now, if we replace this y of x by x, we can find j of x equal to half. And if we replace y of x by e raised x, you can get the value as e minus 1. Similarly, if you replace y of x divided cos of pi of x, you can get the value as 0. But in all the cases, you can just keep in mind whatever the functions we are considering here, that all functions must be continuous within the interval 0, 1. So here, the functions 0, 1, x, e raised x, and cos pi, all are continuous functions in the interval 0, 1. So if we consider another example, now question arises: can we always consider the set of all continuous functions, or any type of functions also we may consider for defining this functional? Yes, we can consider other type of functions also. So here, another functional we are choosing which contains continuous as well as derivative function also. So the functional g of x may involve not only continuous function but also its derivative also. Okay. Suppose you are taking another example where the functional will be like this: 0 to 1 x y square y y dash dx. What is m here? M is c101. C101 means set of all continuous as well as derivable function. Derivable function means first order derivative must satisfy within the interval 0 to 1. So here we can take the functional like this: g of y of x h 0 to 1 x y square plus y y dash dx. Okay, this is an example. Or in general, we can write this as f of x y y dash dx. Okay, or f of x comma y comma dy by dx. In the first case, we have taken f of x and y only. So here MB set of all continuous differentiable functions, and differentiable that must be of first order only within the interval 0 to 1. So in this case, you can check different type of functions by taking different type of functions for finding the value of J. Okay, but your functions must be continuously differentiable functions. So here, the basic problem in the calculus of variation or variational calculus is to determine a function y of x such that this functional a to b f of x y dash dx that gives a maximum or minimum value. Okay, whatever with the functions y of x, we are finding from this functional that may be a maximum value or maybe a minimum value. What is f? F is a function that's a known function having three independent variables. Here, first we have taken this one independent variable here, this two dependent variables, this one independent variables. Okay, while we are discussing or while we discuss about the partial type of functionals, then we go for more than one independent variable. So here we have taken one independent variables and two means one dependent variable and the functional g f of x y dash dx. Okay, objective to determine a y of x such that this functional takes a maximum or minimum value for the value of y of x. Okay, this is our main objective. That means we will extremize this functional to get a value of y of x. Okay, so for this, first we have to derive this Euler equation. Okay, so let us discuss the Euler equation. So consider a functional j that's of the form of f of x y dash, where a and b c1 0 c1 ab. That means here we'll consider the class of functions which are continuously differentiable within the interval a to b. Okay, and this y takes on a maximum value or a minimum value which satisfy this boundary conditions also. Y of a equal to y naught and y of b equal to y. So we have to remember here, while we are extremizing a functional to get an extremum function y of x, we need certain boundary rules. Okay, such that we can get a particular extremum value. And if there is no boundary conditions, you cannot get a particular extremum value. Okay, in that case, you can get a or general, what we can say, you can get a general solution. So you can get a general extremum value. That may be maximum or that may be minimum, but that depends upon the value of c. But while we are considering a boundary conditions, we can get a particular value that may be maximum or minimum within the interval a to b. Okay, so here we have taken MHC1AB, that is set of all continuously differentiable functions. So our basic aim is to find y of x which takes a maximum or minimum value within the interval within the interval a to b. So here we can say, suppose that y of x is the required function, and we have to choose a dummy function eta x also within the interval a to b, and there is certain restriction on eta x. That means this eta of x must vanishes at the end points. That means x equal to a and x equal to b. Okay, and what are basic objective in study the equation? We are just trying to find out the conditions which can be used to get a extremal value for the functional 1. Okay, so this is the required function that we have to determine. This is a dummy function that also satisfy all the things. That means it's also a continuously differentiable function within the interval a to b, but the value of eta of x that vanishes at the end points at x equal to a, at x equal to b. Okay. Now, suppose for any number epsilon, since we are taking two number of functions, we have to associate these two functions. So we are choosing a epsilon here to connect these two functions y and eta. So then for any number epsilon, the function y of x plus epsilon eta x is also satisfied the boundary, since this is also a function which lies in N. Okay, so if we associate or if we take the superposition of these two functions, it also satisfies this boundary condition. Why it satisfies? Because we have already taken here this eta of x vanishes at the endpoints. That means you can say eta of a equal to 0 and eta of b equal to 0. So if we substitute these conditions in here, we can say this y of x plus epsilon eta x satisfies this boundary. That means y of a plus epsilon eta a, that's equal to ya, because eta a equal to 0. And if we take y of b, so y of b plus epsilon eta b, since eta b equal to 0, you can say the value be y of b. So we can say it's also satisfy the boundary condition. So now we can use this function for finding the extremal value of the functional g. Okay. So now we introduce this function. In equation 1. So now, upon introducing this function in equation 1, it becomes j of epsilon equal to a to b f of x in place of y plus epsilon eta, in place of y dash plus epsilon eta dash dx. Okay. You just remind the maxima minima that you have read in calculus. That logic that I am going to use here. Since j is a maximum or minimum for epsilon 0, we must have dj by d epsilon equal to 0. With the use of dj by d epsilon equal to 0, we can get a maximum or minimum value. dj equal to d epsilon equal to 0, that leads to this one. Del f by del y into eta plus del f by del y dash into d eta by dx into dx equal to 0. That means I have just find out the total differentiation of this equation. dj by d epsilon, so left hand side is 0, and right hand side you have to find out df, that means total differentiation of f. Okay, so I just want to remind you, whenever you are a function, you are taking a function of several variables, and in that case, if you are finding the total differentiation, so you can use the rule of total differentiation. Suppose you are taking a function of xy z, let it be, and you are finding df. So what we can write here, del f by del x into dx plus del f by del y into dy plus del f by del z into dz. So that is the total differentiation formula. That differentiation formula, or that total differentiation formula that I am using here, because this function is a function of several variables, 1, 2, and 3. Okay. So upon using the total differentiation on f, we can write like this: del f by del y into eta, del f by del y dash into d eta by dx. Okay, you can check it. And the first one, del f by del x into dx by dx, that is 1. So that's no meaning of del f by del x here. So you can check. So del f by del y into eta plus del f by del y dash d eta by dx. And since we are taking here the differentiation with respect to epsilon, so we can get the total differentiation with the use of y and y dash only, because there is involvement of epsilon in this y plus epsilon eta and y dash plus epsilon eta. Okay. So this is del f by del y into eta plus del f by del y dash d eta by dx equal to 0. Now, upon integrating the second term, since there is no need to integrating this one, del f by del y into eta, so now we are just going for the integration. Okay. There is no need to integrate this one, del f by del y into eta, because this is unknown, so no need to integrate. But we can integrate this part, del f by del y dash into d eta by dx. Okay. So if we expand this integration, we can write like this: integration a to b del f by del y into eta dx plus integration a to b del f by del y dash into d eta by dx into dx, that's equal to 0. Okay. No need to integrate the first part. We can integrate the second part, and for the integration, we can use integration by parts. So upon using integration by parts, while integrating the second parts, we can write the total integration like this. So this is the first part, del f by del y dash into eta into dx. We are not integrated to the first part. Upon integrating the second part using integration by parts, you can get like this: minus d by dx del f by del y dash into eta dx plus this del f by del y dash eta x, this a to b. That means here we have integrated it completely, and uh, and in which parts the integration is involves, that parts we have separated. So we can write the integration of this value like this: a to b del f by del y minus d by dx del f by del y dash beta dx plus del f by del y into beta x e to b equal to 0. Okay. Now, since we have assumed the value of eta b vanishes at the point of or at the end points, that means at a, b. So we can write here eta of a equal to 0 and eta of b equal to 0. So the total part vanishes at x equal to a and x equal to b. So the remaining part will this one, that is a to b del f by del y minus d by dx del f by del y dash eta equal to 0. Okay. Now, since we have assumed this is a dummy function which is not equal to 0, so we can write here this value del f by del y minus d by dx del f by del y dash equal to 0. Okay. This equation 3 is called a Euler equation corresponding to the functional 1. Okay. That means while you are finding the extremal of a functional j with the using of this class of functions, right? You can directly use Euler function for finding the extremals. Okay. So this is Euler equation which can be used for finding the extremal of the functional equation 1. That is a to b f of x y y dash dx equal to, sorry, integration a to b f of x y y dash dx. So this equation is called Euler equation corresponding to the functional g. Now here we can say it's a necessary part or necessary condition for finding the. Okay, that means Euler equation is necessary for the functional j in one to be a maximum or minimum. While you are finding maximum and minimum, this is the necessary condition that can be used for finding the maximum or minimum. Now, if someone try to simplify this equation 3 more clearly, you can simplify this equation 3 that can be equivalent to this equation 4. That's also you can try. I will send you this materials. It's a second order differential equation. It's a second order differential equation. The solution involves two arbitrary constants that's to be determined with the aid of boundary conditions. Okay. So I told there is a need of boundary conditions. Otherwise, you can get a general solution only or general extremal solution. The solution y of x of this equation 3 is known as extremal, which makes the functional maximum or minimum. Okay. Now, what about the uniqueness of this extremal? The uniqueness depends upon the uniqueness of the boundary value problems or the initial value problem also. But generally here, since we are finding the extremal within a certain boundary, so in all the cases we have to consider the boundary value problem. Actually, in starting, I have told you initial as well as boundary value problem, but finally I am just telling you when you are extremize a functional, you have to choose boundary value problem only, such that you can get the extremum value within a certain boundary. Okay, but if you are taking initial value problem, then you cannot get an extremal, or you cannot say this value be extremal within this boundary value point, boundary value problem, or within the boundary points A to B, because whatever the functions you will get in IVP, that function must be lies within the neighborhood of initial points. Okay, so there may be other values in the neighborhood of the endpoints also. So while we are dealing with extremal or extremum of functions, we have to consider boundary value problem. Okay, so depending on the boundary conditions, these extremals that may exist uniquely, may not exist uniquely, or may exist infinitely. As I told, the uniqueness of extremal depends upon the uniqueness of solution of boundary value problem. Okay, if your solution is unique in the boundary value problem, so the extremal should be unique. If your solution is not unique, that means it may gives infinite number of solutions. So it may exist infinitely many extremals. No solutions implies no extremals. So the extremals closely related to the solution of boundary value problems. Okay, uniqueness of boundary value problems or uniqueness of solution of boundary value problems implies uniqueness of extremals of the functional G. Okay, solution unique implies extremal unique. Solution infinitely many solutions implies infinitely many extremals. No solution implies no extremals. Okay, so our final remark is here we can say in extremum or in extremizing a functional, we need a boundary conditions rather than the initial conditions. Okay. Suppose you are taking an example here, j equal to 0 to pi by 2 y square minus 1 square dx. It's a function f that is y square minus y square. Okay, which contains set of all continuous differential function within the interval 0 to pi by 2. Conditions y of 0 equal to 0 and y of pi by 2 equal to 1. So since we are trying to extremize this functional j, directly we can use Euler equations because Euler equation is a necessary condition for finding the extremal of a functional j. Okay, so we can directly use Euler equation. So Euler equation says that's equal to del f by del y minus d by dx del f by del y dash, that's equal to 0. Okay, so first we have to point out the function that involves in a functional. After finding the after point out the or after pointing the function, we have to find out del f by del y as well as del f by del y dash. Okay, after finding del f by del y dash, del f by del y dash, del f by del y and del f by del y dash, we can evaluate this Euler equation. So here we can say f equal to y square minus y square del f by del y, that is minus 2y, del f by del y dash 2y dash. Upon substituting this value of del f by del y and del f by del y dash in the equation, you can get this is minus 2y minus d by dx 2y dash, that's equal to 0. So if we try to simplify this one, you can write this like y double dash plus y equal to 0. Now you can see this differential equation with the condition y of 0 equal to 0 and y of pi by 2 equal to 1, it's a boundary. So the uniqueness of this extremal depends on the uniqueness of this boundary program. That means y of 0 equal to 0, y of pi by 2 equal to 1, and the differential equation y double dash plus y equal to 0. So let us see the solution. If we find the solution of y double dash plus y equal to 0, it gives the solution as this one. Y of x equal to a sin x plus b cos x. Okay. As you know how to solve differential equations, you can find out the solution easily. Now upon using the boundary conditions, y of 0 equal to 0. Here what happens? Y of 0 equal to 0, so left hand side is 0. X equal to 0, this sine 0 is 0. B into cos 0 will be 1. So b into 1 equal to 0, so b equal to 0. So for using the second conditions, we have to neglect this b, and only the second general solution that available, that is y of x equal to a sin x. And in y of x equal to a sin x, if we use y of pi by 2 equal to 1, it becomes 1 equal to a into sin pi by 2. Okay, 1 equal to a into sin pi by 2. Since sin pi by 2 equal to 1, so we can say a into 1 equal to 1. So it gives the value of h a equal to 1. So here you can say the general solution of this boundary value problem is y of x equal to sin x. And if you think about the extremal, here you can say y of x equal to sin x is the extremal. And if we say about the uniqueness of this extremal, you can say the extremal is unique. Okay. Now let us go for another example. J equal to 0 to pi, y square minus y square dx, y of 0 equal to 0 and y of pi equal to 1. So only there is a change in the boundary conditions. Here we have taken the boundary 0 to pi by 2. Here we have taken, we have just extended the boundary from pi by 2 to pi. Okay, you just imagine, that means initially we have taken the boundary as 0 to pi by 2. Now we have extended up to pi. Now when extending up to pi and trying to solve this boundary value problem, here also you can get the same Euler equation, since we are taking the functional same. Sorry, function same, y square minus y square. Here also the function be y square minus y square. Okay. So if you find the Euler equation, it will give you y double s plus y equal to 0. The solution will be y of x equal to sin x plus b plus x. But the boundary conditions are different here. Y of 0 equal to 0 and y of pi equal to 1. So initially we have seen here y of 0 equal to 0, that leads to b equal to 0. So the second condition, general solution that remains here, y of x equal to a sin x. And if we use this y of pi equal to 1 in y of x equal to sin x, what it gives a into 0 equal to 1. A into 0 equal to 1, that means it gives you no information about the solutions. So implies no solutions for this boundary value problem, y double dash plus y equal to 0 with the conditions y of 0 equal to 0 and y of pi equal to 1, implies no extremals of the functional within the interval 0 to pi. Okay. Next, we'll see about the infinitely many extremals. Okay. That comes from infinitely many solutions. So here also, what we have done here in the functional the same, conditions, boundary also same, but we have just changes the conditions here. In second example, we have taken the conditions y of pi equal to 1, but in third conditions, we have taken y of pi equal to 0. Okay. So if you try to solve this boundary value problem here, this one, initially you can get b equal to 0, but while we are trying to solve the y of x equal to sin x, here we can get a into 0 equal to 0. Okay, a into 0 equal to 0, it's valid, no problem. But here, whatever be the value of a, it will satisfy a into 0 equal to 0. That means we can take infinitely many values for a here. So we can say the solution, general solution that takes the form y of x equal to sin x, it's like a particular solution also, which leads to infinitely many solutions. Okay, since we are getting infinitely many solutions in boundary value problem, it leads to infinitely many extremals in the extremal problems or in the functions. So one remark is that extremals not only depends upon the boundary value problems, it depends on the boundary conditions also. Okay, since in second one we have changes the boundary, we have taken the boundary conditions as y of pi equal to 1, and in third one we have changes the boundary conditions from y of pi equal to 1 to y of pi equal to 0, such that we have there is a change in the uniqueness of extremals also. So here we can say extremals depends upon boundaries as well as boundary conditions. Okay, if we extend the extremal, if we extend the boundaries, there may be some variations in extremals, as well as if we change the boundary conditions also, there may be changes in the extremals. Okay, so whatever be the variations that occurs in the extremals, that all arises within a boundaries that initially we are taking a to b. Okay, and extremals that can be valid in boundary value problems only, but in initial value problem we cannot say about extremum of functions. Now, if we further simplify that Euler equation, you can simplify like this also. This also you can try it in equation 5 form. Why there is a need for write equation 5, that I am just going to say here. So in equation 3, the Euler equation will be like this. del F by del Y minus d by dx, del F by del Y is equal to 0. From equation 3, we can get an information about the Euler equation when the function is independent of y. Okay. Suppose whatever is the functions we are taking, if the function is independent of y, then what happens? This del F by del Y equal to 0. The remaining be d by dx, del F by del Y is equal to 0. And upon simplifying, you can get del F by del Y is equal to c. That means you can use the Euler equation directly like del F by del Y is equal to c when the function is independent of y. Okay, no need to take the whole Euler equation. Similarly, after simplification of equation 3, we are getting an equivalent equation. This is equation 5. It's also Euler equation. Here you can see if the function is independent of x, then here del F by del x equal to 0. The remaining conditions, that is d by dx, f minus del F by del y dash into y dash is equal to c. And further integration, that gives f minus del F by del y dash into y dash equal to 0. Sorry, constant. D by dx, f minus del F by del y dash y dash equal to 0. And upon integrating, we can get f minus del F by del y dash into y dash equal to c. So these are two conditions when function is independent of y or independent of x. These are two conditions. One is when independent of y, we can get the Euler equation like this, del F by del y is equal to c, and we can use directly this Euler equation while we are extremizing that function. Okay, and if f does not depend on x, we can directly use this as a Euler equation, that is f minus del F by del y dash into y dash equal to c. So these equations are very useful when this function f is independent of x and y, independent of x or y. Okay. Suppose you are taking an example here, y into y dash cube dx. Conditions, boundary conditions, y of 0 equal to 0 and y of 1 equal to 1. So if we see this function f, you can see this function is independent of x. Okay. Since this function be independent of x, no need to use the direct Euler equation. We can use the modified Euler equation here, that is f minus del F by del y dash into y c for finding the extremals. So here Euler equation be f minus del F by del y dash into y dash equal to c. Upon using f, we can get here this is the simplified portion, y into y dash equal to constant, or upon solving this one, we can get y to the 4 by 3 plus 4 by 3 k to the 1 by 3 x plus c1. You can find out this solution after solving this one. And upon using the boundary conditions, y of 0 equal to 0 and y of 1 equal to 1, we can get the solution like this, which is the extremal of this function. Okay. Here you can see it's a unique extremal. Y equal to x to the 3 by 4 is the z curve, which is the unique extremal. In next class, I will show you by graph also how extremals look like in a plane. So similarly, if we find the extremals of this one, j equal to a to b, this one, you see here, this function is independent of y. Okay. So here, since this function be independent of y, so here directly we can use this one. Del F by del y equal to 0. So del F by del y is equal to c with the Euler equation. Okay. So upon using this Euler equation, del F by del y is equal to c, and upon simplifying and solving, we can get the solution like this: x square plus y minus beta whole square equal to c square. Okay. So since there is no conditions here, we cannot find the maxima or minima here. We can say it's a general extremal or general extremal. That's the form of x square plus y minus beta whole square equal to c square. Okay. So here in this class, we have studied about the extremals and how to find extremals and what are the conditions for finding extremals and what are the restrictions of extremals. Okay. So in next class, we'll proceed further and I will send you the materials in Google Classroom. Okay. Whatever the equations that I have written here directly that you have to simplify and calculate by yourself. And whatever the doubt that arises in your calculation, you may ask in the class. Okay. So now I just conclude here. If any query, now you can ask. And about book, that also I will inform you in the Google Classroom, so that you can get the name of the book and the reference book also that you can follow for the study of the total calculus of variation that you will. Okay.
So you will be uploading the material on Classroom?
Yeah. I will upload the material also.
Sir, a few students had a suggestion. I mean, that if we could move the classes to Microsoft Teams, because then it becomes more convenient to get the recordings of the classes.
नहीं, actually इसमें भी recording हो जाता है.
सर, वो आपको एक परमिशन फिर देते रहना होगा कि मतलब कोई भी एक्सेस अगर करना चाहता तो.
देखो एक्चुअली क्या है, अभी लास्ट सेमेस्टर में पूरा गूगल क्लास इसमें गूगल मीट में मेरा चला, तो माइक्रोसॉफ्ट में थोड़ा मुझे कंफर्टेबल नहीं होता है. तो इसमें आई थिंक कि इसमें तो कोई प्रॉब्लम नहीं है तुम्हें गूगल क्लास में.
ठीक है, तो फिर आप मतलब रिकॉर्ड कर दीजिएगा और हमको रिकॉर्डिंग भेज दीजिएगा, मतलब ड्राइव लिंक आप दे दीजिएगा हमको. ठीक
है, तुम्हें रिकॉर्डिंग भी चाहिए तो भेज दूंगा. तो आज का तो देखो एक्चुअली क्या है, जो कॉमन वाला जो अपना लिंक रहता है ना, कॉमन वाला लिंक में इसमें रिकॉर्डिंग नहीं होता है. मैंने अभी ट्राई किया तो रिकॉर्डिंग नहीं हुआ. सो अभी क्या करूंगा, नेक्स्ट क्लास से तुम्हें लिंक भेजूंगा सो दैट वो मीटिंग में जाएगा तो लिंक क्या होगा, रिकॉर्डिंग होगा उसमें.
ठीक है सर, चलेगा.
ओके, तो मैं लिंक भेजूंगा, उसको रिकॉर्डिंग करूंगा. अगर तुम्हें लेक्चर चाहिए तो उसको भी भेज दूंगा.
ठीक है सर. थैंक यू सर.